Okay, let's continue. And that's the equation. And how can we describe a curved line in the mass element? Okay, not only the curved line in the real element. And remember, we can always, we have already learned the technique, map a curved line to a straight line. And also we can use the inverse map. The inverse mapping, we can map the points in the mass element back to the curved line. So right now we can do the second mapping. Okay. Okay, so let's map the three sets of the coordinates: c1, eta1, c2, eta2, c3, eta3. We can map these three sets of the coordinates in the mass element to the zeta axis. And we can map the c1 eta1 to zeta equal -1, c2 eta2. Okay, so that's the you can say that we have the first time mapping, and also right now we can do the second time mapping. The second time mapping will map the 3 points in the mass element to the zeta axis. Okay, so that's the things we are going to do. Okay, it's time for you to print the screen. Okay, then let's check how can we calculate the ds in the real element. Okay. And we know the x is a function of the c and the eta. Okay, so we know for this one. So what is the dx? So the dx, we can calculate the dx. First, we can take partial derivative of the x to the c, but then we need to multiply the d c. And also we can calculate the partial x to partial eta, then partial times the d eta. And if for the curved line, for the points on the curved line, okay, if we consider the points on the curved line, we know the c, which is functions of the zeta, and they are the summation cj times phi j of zeta. Okay, since we use the three nodal points to describe the curve line, so also we know all the J. We know all the J, and the phi j, which is the Lagrange interpolation functions, and we can use the three nodal points zeta equal to -1, zeta equals 0, zeta equal to +1. We can use these three nodal points to establish the corresponding Lagrange interpolation functions. And the three interpolation functions can be used, it is multiply time. You need to times these two together, then you can get the Xc on the curve line. Also, you can calculate the eta. Right now, the eta is also functions of zeta. Okay, as long as you know how to establish the two-dimensional interpolation functions. Right now, for this mapping, it is only a one-dimensional mapping, and we need the one-dimensional interpolation functions. It is even easier than the two-dimensional mapping and the two-dimensional interpolation functions. Okay, that's so for the consider the curve line, the Xc and the eta, they are functions of the zeta. They are functions of zeta. If we change the zeta value, then we can trace the change of the Xc and the eta in the mass element. So in the mapping, we map the three Xc and the eta to the zeta axis. Right now, if we change the zeta value, then we can get different Xc and the eta in the inverse mapping, back to the mass element. So we can change the zeta value to trace the change of the Xc and the eta in the mass element. Okay, so that's for the points on the curve line. For the points on the curve line, we can change the zeta value to trace the change of the Xc and the eta in the mass element. Okay, then how do we calculate for this one? Since the okay, so we know we can calculate the d Xc d zeta times d zeta. We can get this. Okay. So we can replace these two back to this formula. Then how can we get the dx? Okay, so the dx will be equal to this one. Also for the dy, okay, also we can calculate the dy functions. Okay, you can print the screen. Okay, then how can we calculate the work done by the distributed loading? And the zeta will be the -1 to +1. Will be the -1, +1. And if we know the zeta, then we can calculate the corresponding coefficient eta. And if we know the coefficient eta, then we can calculate the u and the v values. Then we can calculate the u and the v values. And we know we don't need to do the integrations. We can use the numerical integration. So if we use the numerical integrations, okay, the WK means the weight of the integration points. And if we use the 2-point integrations, the WKs they are always equal to 1. And for the 2 integration points, we need to calculate the integration functions at the integration point. And after we calculate this, we need to change it to the 1/2. Okay, and for this part of the equivalent load vector, the equivalent load vector right now, they are obtained from the distributed load applied inside this element. Okay, okay. Okay, so let's continue. If we got the distributed load on the entire area, okay, let's consider if we like to consider the distributed load which is applied at the entire element. And right now the load density for the input load density Wx and the Wy. Again, the x and y represent the load directions. They are along the x directions or the load direction. It is along the y direction. But right now, the load density must be multiplied by the dA. So we need to multiply the Wx and the Wy by the dA and the area in the real element. That's the okay. So if we can multiply the load density Wx and the Wy by the dA, the area in the real element, then we can get the resultant load. Okay, so we need to multiply the Wx and Wy by the dA, the infinitely small area in the real element. If we multiply the dA to the Wx and the Wy, then we can get the resultant load calculated from the distributed loadings. And these two, Wx, Wy multiplied by the dA, you will get the resultant load along the x direction, the resultant load along the y directions. And if we like to calculate the work done by the distributed loadings, then we need to multiply the corresponding displacement along the x direction, also the displacement along the y direction. Then we can calculate the work done by. Okay, so the dA, we can replace it by the dx and the dy. Since the x and the y, they are the orthogonal coordinate system, so the x is perpendicular to the y. So we can multiply the dx and the dy to get the dA, the area of this. And the dx and the dy, which is also equal to the Jacobian times d cos c and the d eta. Okay, so remember we can use the Jacobian, the determinant of the Jacobi matrix, and for all elements, we can calculate the Jacobi matrix and the corresponding Jacobian at any point inside. The element. Okay, so that's the way we can calculate the work done by the applied loadings. And also remember, we have the mapping and the inverse mapping between the real element and the mass element. And it is always more convenient to consider the corresponding area or the corresponding line in the mass element. It is, since all functions, they are defined in the mass element. You cannot get the functions related to the xy directly, and you need to solve the inverse functions. And sometimes they are not so easy to get the inverse functions. Okay, so the dA can be changed by the dx and the dy, and the dx and dy can be changed by the Jacobian times d cos c and the d eta. Also remember the area cover the entire element in the xy coordinates. We can use the area in the mass element. In the mass element, both cos c and eta okay, we know the area in the mass element, both cos c and eta, they should change from the -1 to +1. Okay. If we change both cos c and eta from -1 to +1, then we can cover the entire area in the real element. And it is a two-dimensional integrations. We can still use the Gaussian quadrature, but it is you need to use for example, the 2x2 rule to calculate the two-dimensional integrations, or you can use the 3x3 rule to calculate the Gaussian quadrature. If we use the 2x2 rule to calculate the results, then totally you got 4 integration points. For all these 4 integration points, we know the cos c and the eta. Actually, both cos c and eta, they are the negative square root of 1/3 or positive square root of 1/3. you need to interchange the cosi and the eta. Then totally you can get the 4 integration points. For the if you use the numerical integrations, that's the function values, and the function values, they are functions of the cosi and the eta. For the integration points, we know the cosi and the eta. Then we can calculate the corresponding function values. Okay, the function values, the matrix or the scalar, which is the function of the cosi and the eta, it will be the uv values. And when we calculate the u and the v, part of the formulation, they use the unknown nodal displacements. So when we calculate the uv inside an element, we need to use the nodal displacement of this element. Also, we need to use the shape functions. If we use a 4-node element, then there are 4 corresponding shape functions. And we need to multiply the unknown nodal displacements by the corresponding shape functions. Then we can calculate the u and the v inside an element. So the u and the v, they are functions of the cosi and the eta. The wx and the wy, most of the time we consider they are the constants. And the Jacobian values, they are also it is another one which is functions of the cosi and the eta. So for different locations inside the element, the Jacobian could be different, and the Jacobian can be calculated in real numbers. Since we know all the xi and yi, and also we know all the shape functions, and also we can calculate the partial derivatives of the shape functions. Then we can calculate all elements in the Jacobi matrix. After we calculate all elements in the Jacobi matrix, then we can calculate the determinant of this matrix. Then we can get the Jacobian. Okay, so then we can use the okay, so we can calculate the function values. Okay, and multiply it by the 2 corresponding weights along the cosi and eta directions. And most of the time we consider the constant wx and the wy for problems. And so the wx and the wy could be the constant. So for the entire element, we have the same wx and the wy, but sometimes we have the variable the variable load density problems. If okay, take a picture, and then I will erase. Okay, the question is how do we variable wx, wy. Okay, sometimes we know for some problems the wx and wy, they are not constants. It is also possible for the distributed load applied on a curved line. But let's consider the distributed load applied over the area over the area. If the wx and the wy, they are variables, most of the time the program Okay. If the Wx and Wy, they are not constant inside the element, then we can ask the user Okay, so for example, if we use the 4-node element, then we can ask the user to input the Wx and the Wy for all the 4 nodal points. We can ask the user to input this type of the information. Then what is the Wx and Wy? Okay, so if the user inputted the distributed load at the nodal points, then we can use the shape functions to get an approximate Wx functions in the entire element. Remember, the interpolation functions, it can be used to interpolate continuous functions inside a domain, and the interpolation functions can be used for any physical values. No matter the physical values, they are the nodal coordinates x and y, or the physical meaning of the function values, they are the nodal displacements ui and the vi, and the interpolated functions, they are the u and the v, the displacement functions. And if we like to consider variable the variable distributed load in an element, then we can ask the user to input the Wxi and the Wyi at all the nodal points. If the program got this type of the informations, then we can use the same set of the shape functions. The shape functions, they are also the interpolation functions. So we can use the interpolation functions to get continuous estimations of the Wx and the Wy inside the element. So if the Wx and the Wy, they are not constants, then for different integration points, we need the Wx and the Wy, they are also variable inside the element. So the function values, not only the u and the v and the Jacobian, they are functions of the locations inside the element. Also the Wx and the Wy, they are related to the locations. So when we do the numerical integrations, we just calculate the corresponding function values at the integration points, then multiply by the corresponding weights, then we can get the approximate solution for the integrations. Okay, so you can print the screen, then I will continue. Okay, then how do we get the global load vector? Okay, the global vector could include several. There are several sources which will contribute to the final load vector. For the first one, it could be the concentrated load. And also, they could be part of the distributed load. Okay, and we need to combine all the contributions, no matter the load vector comes from the concentrated load, and the concentrated load could be the concentrated nodal loads or the concentrated load which are applied inside an element. Also, we could have several types of the distributed load. The distributed load could be the distributed load distributed over boundary line of the elements, or the distributed load which is applied inside an element. Also, we have the distributed load over the entire element, which is related to the area of the element. Also, the area could be part of an element. Then we need to do the mapping and the inverse mapping for the second time, and also the second time the mapping, we need to map to a two-dimensional area. So it is the second mass element, and the second mass element is corresponding to the part of the area inside the mass element. And also, when we calculate the equivalent nodal loads, most of the time we just use the degrees of freedom of one element. But when we consider the global vector, we need to combine the degrees of freedom for the entire structure. So when we consider the global load vector, the degrees of freedom, they are the twice of the total number of the nodal points used for the structure, not only for one element. And after you calculate the local load vector, you need to assemble the elements in the load vector, assemble them into the global vector. It is a similar concept. You can theoretically, you need to expand the local load vector to all degrees of freedom for the entire structure. But the expanded vector, we just add the zeros inside this vector, and add the zeros, it will not contribute to the final values. So we can always just assemble the non-zero values to the corresponding locations. You can get the same results. And that's the concept. How can we assemble the non-zero values of an element into the global vector, into the global matrix or vector? Right now, if we consider the load vector, it will be the local vector into the global vector. Okay, so we can get the final global load vector. Okay, I will wait for you. And the solution procedure, we will calculate the K1, K2, the element stiffness matrix of all elements, and assemble them into the global K. So first we need to calculate the element stiffness matrix remember they are the B transpose times D times B, and multiplied by the Jacobian. Then we can calculate the element stiffness matrix. After we calculate the element stiffness matrix for each element, and then we can assemble all these element stiffness matrix into the global stiffness matrix. And the assembled global K matrix, we need to modify K by the boundary conditions. Okay, so remember we will not consider the boundary conditions at the beginning in the derivation, since if we consider the boundary conditions, then there are several special cases for some elements. For example, if we use the 4-node element, for some elements, all 4 node points, they are related to the nodal points with the unknown displacements, but we know the resultant loading applied to those nodes. For some elements, all the 4 nodes, they are belong to the unknown displacement but the known force. But for some elements, we have 3 points, they are unknown displacements, but one of the nodal points, they are connected to a support. Then we know the displacements, but we don't know the reactions. So when we formulate the displacement functions, we need to consider, for this element, we need to consider only the 3 nodal points which could move. Also the displacements, they are unknowns. But for one of those 4, they are the known displacements, but we don't know the related force. It will make it more complicated. So most of the time when we consider the element stiffness matrix, we will assume all the related nodal points, they are the unknown displacements, but we know the force. So that's the assumptions when we get the assembled global K matrix. But we still need to consider the boundary conditions, since it is not possible for a structure without any support. If a structure without any support, then it is an unstable structure. You cannot solve the problems for unstable structure. The unstable structures, even the applied loadings, they are equal to zeros. You can still see the rigid body motions for the structures. So it is not possible for a structure to solve the solutions without any support. So you can say for all the practical problems, we must have some types of the boundary conditions. But the boundary conditions, usually we will consider them after we assemble the global K matrix. So after we assemble the global K matrix, then we need to consider the boundary conditions. There are several methods we can use to consider. The basic methods, we can just eliminate corresponding rows and columns. And for the MIT's method, we can modify the off-diagonals to the zeros, the diagonal element to be the 1. And the Berkeley's method, we just add very large numbers to the corresponding diagonal elements. Okay, so that's the methods we can use to consider the boundary conditions. So we have the original K, and we have the K which is modified. Okay. Also, we need to calculate the P1, P2 and assemble them into the global P matrix. Okay, and for some methods, the modification methods, not only the K matrix will be modified, also the load vector could be modified. Okay, so that's the procedure. We need to calculate all the element stiffness matrix, assemble them into the global K, and also we can calculate all the load vectors and assemble them, all the local load vectors, and assemble them into the global P vector. And we can use some methods to modify both K matrix and the P vector. Okay. After we finish all these procedures, then what is the total strain energy? Okay, right now all vectors and all matrices, they are the global vectors and the global matrix. So the U displacement vector, they include all the nodal displacements of the structures. And the global K matrix, they include all the degrees of freedom for the structures. The global load vector and the global U vector. Okay, then based on the minimum total potential energy, the theory of the minimum total potential energy theory, and remember the delta pi equal to 0, which is the theorem of the minimum total potential. Okay, the total potential energy, which is equal to the pi. The first term, which is the U, which is the strain energy of the structure, and the second term, it is the V, which is the potential energy due to the applied loadings. After we calculate all of this, we will find the displacement U, which can make the pi an extreme value. And right now, the extreme value, which is the minimum value, Okay, also remember this theorem, which is an alternative method to consider the equilibrium equations. And the finite element method, most of the time, it will follow the displacement method. For the displacement method, at the beginning, we need to assume a set of the possible displacement functions. And when we assume the displacement functions, they should fulfill the comparability requirements. So for the displacement method, the comparability equations, they are the first set of the equations we will consider. And also the constitutive equations will be used for when we calculate the K matrix, the stiffness of the stiffness matrix of the structure. And since when we calculate the strain energy, we need to multiply the strain by the stress. And the relationship between the stress and the strain, they are related to the constitutive equations. So the correct constitutive equations, they have been considered when we get the K matrix. And the third set of the basic theorem we need to follow when we calculate the structural analysis, it is the equilibrium equations. And the equilibrium equations can be replaced by the theorem of the minimum total potential energy theory. So when we calculate the delta pi equal to 0, actually we are considering the equilibrium equations. And how do we calculate the delta pi? Okay. Okay, so the delta pi means that we will take a variation to the pi functions. The variations means that we will vary anything which can be changed. And in these derivations, right now the u vector, the elements in the u vector, they are the unknown nodal displacements. And for all the nodal displacements, we did not specify special values to them, and we like to keep the u. They are the unknowns. So the u vector, elements in the u vector, they are the values can be changed. Okay, I think let's take a break here, and I will continue.